All right, we're going to finish up complex numbers, okay, section A4, just the second part. So yesterday we did adding and subtracting. Today we're going to do multiplying and dividing. All right, so yesterday we said that that's a definition, right? I equals the square root of -1. That's a definition, not something you can prove. Does anyone remember what we said about I squared? What does I squared equal? -1. Yep. So anytime we do a problem, if there's an I squared in the arithmetic we're doing, do not leave it as I squared. Okay. Always change I squared to -1. I just said that. All right, so let's look at how we multiply two complex numbers. Okay, basically what you would do if you want to multiply these together is that. Does anybody recognize that pattern of multiplying? Yeah, it's like some people call it FOIL, or some people like the distributive property twice. You do it twice. But that's all you're really doing. You do the distributive property. So if we were going to do this all out, you multiply A times C, and then A times DI, C times BI, and then BI times DI. Multiply all that out. And when you do that, there is one multiplication that's going to result in an I squared. It's when you multiply the last term in each parenthesis together. And we just talked about what you have to do with that. Okay, so whatever you call it, that's the pattern you follow to do it. Okay, other than that, there's really nothing else to say about multiplying. Okay? If you know how to multiply these two things together, then you can multiply complex numbers, no problem. Okay, let's look at an example. Right, so let's multiply 2 plus I times 1 minus I. Okay, does everybody have what's up above? Anybody need your copy? Alright, so Peter, can you tell me first thing I would do?
2 times 1.
Yep, we're going to start with the real part, so 2 times 1. And what I'm going to do is I'm just going to write it as I go. If you want to write 2 times 1 and then simplify after, you can, but I think it's easier just to do that as you go. Haley, what would be the next thing I would multiply?
2 times 5.
Yep. 2 times, what is that again?
So -2.
Careful, 2 times -I. What would you get if you did 2 times -x? X, right? Yeah, you're gonna put the other thing you're multiplying with it. So 2 times -I would be -2i. Yep. Okay, and Connor, what about the next 2 I would multiply?
Be 1i.
Yeah, I'm gonna multiply 1 times I. Now we've got some like terms we can deal with after.
And then -I squared.
Yeah, and then we have, first of all, a positive times a negative. Positive times negative is negative. I times I, exactly what Connor just said. I squared. Okay, so a few things we need to deal with. One, we can't leave I squared. 2, we want to combine like terms. So Eric, can you tell me what I get when I combine -2i plus I?
-I.
Yeah, think of that as -2 plus 1. It's -1i. Or if you want to write just -I, that's fine. All right, now we have minus, and now we're going to change I squared. Paige, what did we say I squared equals again? Negative 1. Okay, so I have a negative from the original problem. That's what's in front. And then I get another negative from the I squared. Okay, Rhonda, what's going to happen there? Minus 1.
Turn into a plus.
Going to turn into a plus. And then, Alex, my last step would be to combine anything I have left that's like terms. So what would I get when I combine there for a final answer?
3 minus I.
Yes. That's how you multiply two complex numbers. So your final answer should always have this format. You have a real part, a plus or a minus, depends on the problem. Another number right there, and then next to it, an I. That's how every answer should always look. In this case, if you're like, well, what's the number in front of I here? It's like having a negative 1. Normally, we don't write that when it's a 1. But you can, and that's fine too. Okay. Questions on that one? Okay, let's try this one. So we have 8 plus I times 3 plus I. Emily, first thing I would multiply?
8 and 3.
Yeah, which would give me
24.
24. Irene, the next thing?
8 times I.
Yep. And 8 times I gives me
8I.
good. 8I. Emily, the next two?
5 and 3.
Yep. And what does that give me?
3I.
Very good. And Connor, the last two?
2 I's.
Yep.
The I squared.
Positive I squared or negative I squared?
Positive.
Positive, because it's a positive times a positive, which is a positive. Hey, Hayden, anything there that I can either combine or I need to change?
8I and 3I.
Yep, we can combine that. And what do you get?
11.
Yep, 11I. So 11I. Rudy, anything else there that I need to deal with or I could deal with at this step?
I squared.
Yep.
Minus 1.
Right, I squared is going to change into a minus 1. Last step, combine your like terms. So this number has a real part of 23 and an imaginary part of 11. Okay. Any questions on it? All right, so now we're going to look at multiplying again, but we're going to look at something special, okay? Kind of a special case where a lot of stuff happens to cancel out. So suppose you have a complex number. Okay, I'm just going to call it Z. Okay, my complex number is Z. It has a real part, which I'm calling A, and an imaginary part, which I'm calling B. If you write this symbol, Z with a bar on top of it, that symbol is called the conjugate. That's the way you pronounce this. It stands for the conjugate of Z. That's how you pronounce it, but it still doesn't tell you what exactly, like mathematically, you do to get the conjugate. Does anybody know what the conjugate is? Okay, conjugates come up when we study complex numbers. They're going to come up again next week when we do trig identities too. So a conjugate, all that means is if you look at the imaginary part, it's a plus bi, you change the sign of it. You make it minus bi. If it was already minus to begin with, when you change the sign of it, it would become positive. So all you have to do to find the conjugate of a complex number is change the sign of the imaginary part. That's what negate means. Just a shorter way of saying change the sign of. You don't do anything to the real part. You leave that alone. Okay, so I've got some examples where we'll look at a complex number and then we'll practice finding the conjugate of that. And in a minute, you'll see what the conjugate is actually used for. It has something to do with division. All right, so if I had the number 3 plus 4i, anyone think they could tell me what the conjugate of 3 plus 4i would be?
3 minus 4.
Yeah, it would be 3 minus 4i. All right, how about if I had negative 8 minus 2i? What would be the conjugate of that? Alex?
Negative 8 plus 2i.
Yep. Negative 8 plus 2i. How about 5i? I don't think they know what the conjugate of 5i would be. Yep.
Negative 5.
Yep, negative 5i. And how about 3?
Would it just be 3?
It would be 3. Okay? And if you're like, well, wait, why does that stay the same? Think of 3 like this. It's 3 plus no imaginary part. Well, conjugate is 3 minus no imaginary part. Okay? So it stays the same, 3. So any question on, if you're given a number, how you find the conjugate? All right, so now let's look at what happens before we do division. If we multiply 2 conjugates together. So the problem here is asking you to take whatever number they give you and multiply it by its conjugate. Okay, the number they're giving me is 3 minus 4i. So the conjugate would be 3 plus 4i. Now I want to multiply those together. And I want to see what happens. Okay, so the first thing I'd do is I'd start with 3 times 3. Zach, what does that give me? 9. And then I'd have 3 times 4i, which is 12i. And 3 times negative 4i. What's that going to be? Negative 12i. Okay, so we'll come back to that in a second. You know, we can simplify something there. And then we have negative 4i times positive 4i. Yep.
16 squared. That's negative.
Right, it's a negative times a positive, so it's a negative 16i squared. Hey. Anything there that we can simplify? What? Something's going to happen, yep.
12i just goes to I.
Right, 12i, negative 12i, what does it go to?
Just I. Or would it be 0?
0, right? We have 12i, take away 12i, you've got 0. Okay. So that's gone. That always happens with conjugates, right? So you don't need to bother doing the outer and the inner. I mean, you can, but that's going to happen every time. They're going to cancel out. All right, so let's see what we have left. 9 minus 16 times I squared. But what's I squared again? Negative 1. So we have 16 times negative 1, which is negative 16, but we're subtracting it. So what's going to happen if you subtract negative 16? It's going to turn positive. So really, we're doing 9 plus 16, and the answer we get is 25. What kind of number is 25? I mean, it's lots of kinds of numbers, but I'm thinking of something term related to what we're studying right now. Yeah. Okay, it is a whole number. What else is it? Yeah.
Counting number?
Yes, it is a counting number.
Square.
It's a perfect square. Yeah. What else is it?
Is it rational?
It is. What do we study? What's this section all about?
Real numbers?
Complex.
This section is about complex numbers. What kind of number is that? It is complex. Can you be a little more specific? What kind of complex number? Yeah?
Imaginary.
It's not imaginary.
It's a real number.
It's a real number. Yes. I think you said rational.
Yeah, I said real number.
Ah.
Then you said close.
So it's real. So the point here is if you multiply conjugates together, all the i's disappear. Okay, that's the point. You only end up with a real number. So the shortcut, okay, for multiplying conjugates in your head, all you have to do is take the first number, square it. Take the second number. It doesn't matter if you take the negative with it or not, because you're going to square it. It just goes away. Take the second number, square it, add them up. That's all you have to do. First number, square it. Second number, square it, add them up. Okay, so let's see if we can do this one using the shortcut. What do I get when I square the first number?
25.
25. Square the second number.
16.
Yep, 4 squared is 16. Add them up. Done. Okay. If you don't like the shortcut, you can FOIL the whole thing out. But that's exactly what's going to happen. Okay. And I'm going to use that shortcut when I do division. Any question on the shortcut? Okay, you can't use this all the time. You can only use it for conjugates. Right? If you have to multiply two things like that, you're still going to do it out the old way. This shortcut works for conjugates. Okay, so the formula to multiply two conjugates. If that was your complex number, again, A and B would be numbers, but in general, if the real part was A and the imaginary part was B, square the real part, square the imaginary part, add them up. And in general, we always use the idea of conjugates when you want to cancel stuff out. Whether you're dealing with complex numbers and you want to cancel out imaginaries, or you're dealing with trig functions and you want to cancel out part of a trig function. Conjugates are always used to cancel things out. Any questions on that shortcut? Okay, so now let's see where we're going to use that. Okay. The reason we need to conjugate is because when we divide, you're not allowed to leave imaginary numbers in the bottom of a fraction. Okay, ever. Just like you can't leave square roots there, you can't leave I there. So we need a way to get rid of all the i's. How can you cancel out all the i's? Conjugates. Okay, so that's why we're going to need it. So, in order to divide two complex numbers, you're going to multiply the top and the bottom of your fraction by the conjugate of what's in the bottom. And what that's going to do is it's going to wipe out all the imaginary numbers in the bottom. It's going to put them in the top, but that's fine. You just can't leave them in the bottom. Okay, so really, to do division, you need to understand multiplication. That's all division with complex numbers is. It's multiplication by the conjugate. Okay, and you always do the conjugate of the bottom. You don't do the conjugate of the top with these kinds of problems. Okay, because you want to cancel the i's out from the bottom, not the top. Okay, so we'll look at couple examples with division, and then that'll finish up our review of complex numbers. Okay, so I want to divide 1 by 3 plus 4i. Now, this one's not as bad because in the top, it's just a single number. We're going to do one like this next, where the top is complex and the bottom is complex. But this one's going to be a little quicker. Okay, so the directions say multiply the top and the bottom by the conjugate of what's in the bottom. What's the conjugate of what's in the bottom? Yep.
3 minus 4.
3 minus 4i. So we're going to multiply top and bottom by 3 minus 4i. Now in the top, normally it would be a FOIL, and in the next problem it will be. In this one, it's not. It's just a single distributive property. And in fact, you're only distributing a 1, so is anything going to change? No. So the top is 3 minus 4i. And now let's use our shortcut to do the bottom. What's 3 squared? 9. 4 squared? And then add them up. So what do we get in the denominator? 25. Now, if you leave your answer like that, that is not standard form. You're supposed to have, like I said before, real part, plus or minus, imaginary part. You're not supposed to have the whole thing over a number. So what we're going to do is just separate it into 2 parts. The real part is going to be 3/25 minus, because I have a minus up above. And the imaginary part is 4/25. Now I've written it in standard form. Okay, so on the test, if you multiply, final answer always needs to be written this way. Any question on that? You could put the I in the top if you want, or you can put the I right in the middle. Most people put it in the middle. It's kind of like when you do y equals mx plus b. When you have the letter x, usually you put it right in the middle of the fraction. It's not wrong if you do this. It means the same thing. It's just the first way is more common. Okay? So that's how I'm going to do it here. Just put the I right in the middle. Okay. All right, so let's try this one. So you got 1 plus 4i divided by 5 minus 12i. Cameron, what's in the bottom here?
5 minus 12i.
Yep. And what would be the conjugate of that?
5 plus 12.
5 plus 12i. So I need to multiply it on the bottom. That's going to be quick. On the top, it's not going to be too bad, but there is no shortcut. We have to just do it out. Can anybody tell me what we're going to get in the bottom? 169. We're going to have 25 plus 144. So the entire bottom is done. 169. Now the top, we'll just do that out. So we've got 5. And let's do the next part and combine at the same time. We get 12i plus 20i. What's 12i plus 20i? 32i. And now the last part, we're going to get positive 48i squared. Well, what number is 48i squared? Yep, which is negative 48. Okay, so combine like terms and then split it into real part and imaginary part. We have 5 minus 48. Yep, negative 43. And what's the denominator going to be? Yep, 169. That's your real part. Plus, because the imaginary part was positive, 32 over 169. And don't forget to put your I. If that fraction reduced, you could reduce it. That one doesn't. But if you had a fraction like, I don't know, 5/10, you'd want to reduce it to 1/2. Okay, so always reduce it if you can. Okay, so any questions on dividing? All right, so it's not too bad. I mean, it's pretty easy to follow. You just have to use FOIL. But if we know how to write complex numbers in polar, I can make everything you just learned go away. You don't need any of it. You don't need all this foiling, combining like terms, changing I squareds to -1s, then just separating it into two separate fractions. That can all disappear if we know how to do complex numbers in polar. So that's the last thing we're going to look at in section 5.3. All right, so the first thing they do in 5.3, it's a little bit separate from what I just mentioned, but it's graphing complex numbers. And if you know how to graph on an XY grid, graphing complex numbers is super easy. Instead of calling it the X and the Y axis, they call it the real and the imaginary. Real axis is horizontal, imaginary is your vertical. And if you forget which one is which, just think about when you write it as a regular coordinate, the horizontal is always first, the vertical is always second. Go back and look at one of our answers. The horizontal is always first, the vertical is always second. The horizontal is your real, the vertical is your imaginary. Okay, so it follows the same pattern as XY. All right, so let's see if I give you a point, if we can graph it. It's a 2 plus 3i. Matt, what's the real part in that number?
2.
2. So we're going to start by going 2 units on the real axis. Positive and negative is exactly the same. Positive is right, negative is left. For the vertical, positive is up, negative is down. All right, so we're going to go 2 units to the right. And then Victoria, my imaginary part is, yeah, just the 3. So we'll just focus on that. And that's going to be 3 units on the imaginary axis. Which way?
Up.
Up. So you're going to go right 2, up 3. And that's the point. 2 plus 3i. That's it. Let's try 4 minus 8i. Alex, could you tell me on the real axis first how many units?
4.
And then which way?
To the right.
4 to the right. And then in the imaginary axis, how many units and which way?
8 down.
8 down. So 4 right, 8 down. Right there. So that's 4 minus 8i. Ileana, how about that one? -8. 8 to the left, and then how about up and down? It's right on the axis, right? You think of it as plus 0i. There's no up and down here. So it's like graphing -8, 0. It's -8. And 5i. Katie, how would I graph 5i?
You would go up the imaginary 5.
Yep. Any left and right here? No? It's like 0 plus 5i. 5i. Any question on graphing complex numbers? All right. So now the last thing we're going to look at is what I mentioned that most of this section is about, is how do you write complex numbers in polar? Okay, how would you graph something like that on a polar grid? Okay. So the way you've been writing complex numbers, that's what we call rectangular. Why is it rectangular? Because you're moving on a rectangular grid. Like the first one, you're moving 2 units right, 3 units up. That's not an angle, and that's not a radius. If you put a radius and an angle in there and convert it somehow, then it's polar. Okay, but until you have radiuses and angles, that's not polar, that's rectangular. And most of the time I've been using A and B to represent the real and imaginary part. I'm starting to switch those letters now because we're getting into graphing. That's why I'm using X and Y. Technically, it doesn't matter what letters you use. But I think if you use X and Y, you'll make the connection with graphing easier. That's why I'm using X and Y. Okay, also, if you look at where the I is, do we usually put the I before the letter? No, you don't normally do that. For the formula that I'm about to show you, your book does that. Okay, that's why I put it. But technically, that's the same. Okay? But I'm just trying to make what I do match what's in your book. So that's the rectangular form. Okay. Now we're going to look at how do we write that in polar. Can someone remind me again, what are the 2 things you need in polar? For rectangular, you need the X and Y. For polar, you need
Radius and an angle.
you need a radius and an angle. So somehow, we need to make that and that disappear. Well, we have formulas that we learned earlier in the week to do that. And we can use the exact same formulas from section 5.1. Does anybody remember the formula for X that converts it into a radius and an angle? Yeah?
X squared plus y squared is the square.
What's that? Yeah, I didn't hear you.
Is it x squared plus y squared?
Okay, that was
Oh,
in
wait,
the
no,
same
it's
section.
Radius, and then
We're going to come back to that. So it starts with radius, and we'll come back to what you said because that is going to be handy for something else.
Times cosine theta.
Yes. X equals r cosine theta. Does anybody remember the one for y? You want to try y? Yeah?
Alright, so there's sine, r sine theta.
R sine theta. Okay, so all you have to do is take that, plug it in where you have x, take that, plug it in where you have y. Okay, so let's make those 2 changes. Okay, so writing that, we would get r cosine theta, okay, plugging that in for x, plus, okay, the I is just going to stay right where it is. That doesn't move. And the y is going to turn into r sine theta. Okay, now if you look at each term, first term, second term, what do each of those terms have in common in front of the trig function? They have an r. So when 2 things have the same thing in common, we can factor it out. Okay, so let's put an r on the outside. What's left in the first term if you factor out r? Molly? Cosine of the angle. Do you remember what Greek letter that is? Theta. Theta. Plus, what if you factor r out of the second term?
Sine theta.
You're left with a little bit more than that. One thing we forgot.
Oh,
The I too. I sine theta. And that's the polar form. You could just you don't have to write it twice. You could just label what you just wrote. That's the polar form of a complex number. It's r cosine theta plus I sine theta. So if you wonder, like, what would a final answer look like in polar? It would look something like this. 3 cosine 45 degrees plus I sine 45 degrees. That's a final answer. You don't do anything with that. If you took the cosine of 45 on your calculator and you multiplied the 3 out, what that would do is it would convert it back to what you started with. Okay, we don't want to do that. So we just leave it like that. So there's 2 things we need to find to write this in polar. You need to know your r and your theta. Now, Rudy was just telling us how we get r. Use the Pythagorean theorem. R squared equals x squared plus y squared. You already have that in your notes. To find theta, that's where you use the inverse tangent y over x. You use the same 2 formulas we just learned yesterday. If theta is in quadrants 1 and 4, would you have to add 180? No. What if it's in 2 or 3? Yes. So again, I'm not going to write them all down again because you already have them. Just put in your notes. See formulas from r and theta from yesterday's lesson. Okay, so let's try this one. So square root 3 minus I. Now here, it's a little tricky because they didn't put in the number in front of I. So what number should be there? You could put in the -1 if you want. Okay. So we've defined r and theta. Now if I scroll back up, okay, remember, the first number is your x. It's like x. The second number is like your y. Alex, can you remind me what the formula is to find r?
To find r is I'm confused.
So this is going to come from yesterday's notes. So this is not, I told you what it was, but I did not write it down again.
This is the square root 1. Or is this the number?
It potentially, depending on how you write it, you would do a square root at some point, yeah.
Oh, this is in quadrant 4, so it'd be. Is this the
It is in quadrant 4, but we don't need to know that for the radius. You do need to know that for what I'm going to ask you next. So hey, I'll come back to you. Hang on to that thought, that we're in quadrant 4. But can someone remind me what the formula is for the radius, no matter what quadrant you're in? Yep.
X squared plus y squared equals r squared.
X squared plus y squared equals r squared. Okay. The I has nothing to do with it. You just use the 2 numbers, don't use the I. So x squared plus y squared equals r squared. Okay. Now we do that out. Connor, what's the square root of 3 squared?
3.
Yep, those just cancel out. -1 squared gives me 1. So r squared equals 4. So what's my radius? 2. I'll come back to that when I write my final answer. And what I'll do is I'll fill in r for 2. The last thing I need is my angle. And it's the same angle you write here and here. You just have to find it once. All right, so Alex was telling us that we went right and we went down 1. That's quadrant 4. Did you get the formula, Alex, for theta in quadrant 4?
Yeah. R cosine theta plus I sine theta.
So that's the form of a complex number in polar, but what I'm looking for is the formula from yesterday. It involves an inverse trig function.
180. Oh no, this is just inverse tangent of x over y.
Inverse tangent of y over x.
Oh, y over x.
Yeah. So we don't add 180 because we're in quadrant 4. We do inverse tangent of y is -1, x is square root 3. Basically, converting this to polar is exactly like converting this coordinate to polar. That's what you would have seen yesterday. Square root 3 comma negative 1, convert to polar. Now it's just written with imaginary, but all the steps are the same. You still got to find r the same way, find theta the same way. All right, so let's type that in and see what we get. All right, so I'm in degrees, so that's fine. Inverse tangent of negative 1 divided by square root 3. And we get an angle of negative 30. What would negative 30 be the same as a positive angle? Yeah? 330. So just like when we did polar coordinates before, okay, there were 4 different ways to write it, there's still a bunch of different ways to write this answer. Okay? You could do a positive radius thing, but generally I try to stick with a positive radius, positive angle. All right, so your final answer, all you have to do is fill in to that formula, and then stop. So we get 2 cosine 330 plus I sine 330. Okay, that's one way you could write your answer. Okay, I'll show you a couple other ways. Second way you could write it is just leave the angle negative. 2 cosine negative 30 plus I sine negative 30. I think that way looks a little more confusing because now you've got a negative angle in there, but that's how you could write it. And the third way is a little different. It's kind of it's a trick to get rid of the negative angle, kind of like we did the first time, but without making the angle bigger. Okay, so the way we did it, we added 360, which is fine, that works. But the angle got really big. So there's a way you can get rid of the negative and keep the angle exactly the same, basically. The radius is going to stay the same. That has to be a 2. Let's look at the cosine of negative 30. That's what you get. Let's look at the cosine of positive 30. What's the difference between those two? The two answers? Nothing. Right, let's just try another one. Let's try cosine of negative 82. And let's try the cosine of 82. What's the difference between those answers? Nothing. So, in other words, whether you take the cosine of a negative angle or a positive angle, the negative doesn't even matter with cosine. So you can just get rid of it. Okay, so a negative with a cosine, just don't even write it. You don't have to. Let's try the same thing with sine, okay, and see if the negative makes a difference there. Okay. Let's try sine of negative 30, sine of positive 30. Are those two answers the same? No. What's different between them? One's negative, one's positive, so it's the same number, different signs. Let's try another one. Sine of 76, sine of negative 76. Did the same thing happen there? Right, so one is a positive, one has a negative in front. So with sine, you can't get rid of the negative, but what you can do is move it in front. So we could change this to minus I sine 30. Right? So with cosine, we just wipe the negative right out. With sine, we couldn't get rid of it. But what we can do is just move it in front. So that's a third way you can write your answer. A little different from what I showed you before. But the advantage here is the angle doesn't get bigger, like in the first one. All three of those are correct. Any questions on that? Okay, if the problem asks for an answer and they're not specific about if the angle should be positive or negative, you can pick any one of those answers. If it was a matching one, then you might have to match what you get to whatever I write. But there will only be one correct answer per problem. Okay, you wouldn't see all of these listed as choices, just one of them. Okay, questions on that? Okay, so the homework tonight, 15 to 27, odd, and 28. That's on the complex numbers, multiply and divide. And then page 333, 11 to 19 odd, that's on what we just did. Okay, and on the page 333, these questions have a couple parts. It says, graph the point, like I showed you right here. So the first thing they have you do is graph it, and then the next thing they have you do is write it in Polar. So there's two parts for each of these.